Count the galaxies in a sphere 1 billion light-years around the Earth, and roughly 1 in 5 that should be there are simply missing, not destroyed, not hidden behind dust, never there at all. For years, a small group of astronomers argued about what that shortfall meant, and then, in 2025, listening to the faint ringing left over from the birth of the universe, they reached a startling conclusion. It may be about 100 times more likely that we live inside an enormous hole in space than in a normal patch of cosmos. So get comfortable, let the day fall away, and stay with me, because we are about to find out what it means to live inside a void. Part 1. The Missing Galaxies. There is a number you can measure about the sky that should not come out the way it does. Take a sphere centered on the Earth and let it grow outward in every direction until its edge sits about 1 billion light-years away. Now count the galaxies inside it, all of them, the bright spirals and the faint smudges and the giant ellipticals, and compare that count to the number the universe says should be there, the average density of galaxies stretched across all of cosmic space. When you do that, something strange happens. Roughly 1 in 5 of the galaxies that ought to be in your sphere are simply not there. They have not been destroyed. They have not been hidden behind dust. They were never there to begin with. And that small, stubborn shortfall is the first clue that we might be living somewhere very unusual. I want to be careful with my words here, because the easy way to say this is also the wrong way. It is tempting to picture a region scrubbed clean, a pocket of true emptiness, a bubble of nothing. That is not what the measurements show. What they show is subtler and, in a way, stranger. The space around us, out to enormous distances, appears to be thinner than the cosmic average, not empty, thinner, as if the universe in our neighborhood was poured a little more sparingly than it was everywhere else. And if that is true, then we are not floating in a typical patch of cosmos at all. We are sitting inside a hole. That word, hole, sounds dramatic, and I promise I am not reaching for drama. Astronomers have a quieter name for it. They call it an underdensity, or sometimes a void, and the particular one we seem to inhabit has a name made of 3 initials and a discovery that almost nobody noticed when it arrived. For years, it lived in the technical literature, argued over by a small number of specialists, while the rest of us went on assuming our corner of the universe was perfectly ordinary. And then, in 2025, the idea came roaring back into the headlines, carried by one of the most unexpected pieces of evidence imaginable. A team of researchers announced that by listening, in effect, to the oldest sound in existence, the faint ringing left over from the birth of the universe itself, they had found that it may be about 100 times more likely that we live inside a void than that we live in a perfectly average region of space. 100 times more likely. Sit with that for a moment. Not a wild guess, not a fringe notion whispered at the edge of science, but a conclusion drawn from 20 years of careful observation, pointing at the possibility that our home is the exception rather than the rule. The void even has a proper name, drawn from the 3 astronomers who first measured it convincingly. It is called the KBC void, and it is sometimes called the local hole, and depending on how you measure its reach, it may be as much as 2 billion light-years across. That is not a typo, and it is not an exaggeration. 2 billion light-years centered more or less on us. So here is the question I want us to follow together tonight, the question hiding inside the title. Are we really living inside a cosmic void? And if we are, just how big is it? And is it bigger than anyone first dared to think? Because the answer, whichever way it falls, does something that very few discoveries in science actually do. It does not just rearrange a map, it reaches back and touches the instruments we used to make the map in the first place. If we live inside a hole, then the universe we measure from in here may be quietly lying to us about how fast it is growing, about how old it is, about what it is made of. Our vantage point would not be neutral. It would be tilted, and we would have spent a century reading the cosmos through a lens we did not know we were holding. There is something else this idea brushes up against, and it goes back much further than any telescope. For 500 years, science has leaned on a humble assumption, the idea that we are nowhere special. Copernicus moved us off the center of everything, and we have been getting more comfortable with our own insignificance ever since. The Earth is not the center of the solar system. The Sun is not the center of the galaxy. The galaxy is not the center of anything. We told ourselves the universe looks the same from everywhere, that no observer holds a privileged seat. And now, gently, almost apologetically, the void hypothesis taps us on the shoulder and asks whether that is entirely true. Not because we are the chosen center of creation, nothing so grand, but because we may have drawn an unusual ticket, a seat inside a rare and enormous emptiness that changes the view. I find this is one of those ideas that rewards a slow, patient walk rather than a sprint. So that is exactly what we are going to do. Over the next couple of hours, we are going to take this apart piece by piece, the way you would examine a strange object you found and could not quite identify. We are going to ask how you even measure something that is defined by what is missing, how you weigh an emptiness. We are going to meet the crisis this void might solve, a single number that has split modern cosmology into two camps that refuse to agree. We are going to understand the beautiful, almost unfair trick by which an empty room can make the entire universe look like it is expanding faster than it really is. We are going to listen to that ancient sound, the one that betrayed the void's presence. And we are going to push all the way out to the edge of what anyone knows, to a radical possibility that some physicists are quietly entertaining, that the lumpiness of the universe has been fooling us about far more than just its expansion rate. None of this is cause for alarm, and I want to say that plainly before we go any further. This is not a story about something coming to get us, or about the sky falling. A void is not dangerous. You cannot feel it, you cannot fall into it, it will not arrive one night and swallow the earth. It is a puzzle, one of the most elegant and far-reaching puzzles in all of modern science, and the pleasure of it is in the slow accumulation of clues, the way each new measurement nudges the picture a little further toward the unbelievable. So, there is nothing to brace against here. There is only something to wonder about. I should also tell you where I sit in all this, because I am not going to pretend to be above the question, lecturing down at you from some certain height. I do not know the answer, and neither, fully, does anyone else yet. That is what makes it worth 2 hours of a quiet night. We are going to walk into this mystery as fellow travelers, you and I, following the same trail of evidence the scientists followed, pausing where they paused, getting uncomfortable where they got uncomfortable. And by the end, I think you will see the universe a little differently, not because I will have convinced you of any one conclusion, but because the question itself does something to how you picture the dark. Because before we can ask what a void does to us, we have to answer a question that sounds almost impossible when you first hear it. How do you measure something that is defined entirely by what is not there? How do you weigh an emptiness, count the galaxies that were never born, and prove that a billion light-year stretch of the cosmos is thinner than it should be? That is where the story really begins, and it begins not with a grand telescope pointed at a single dramatic object, but with something far more patient and far stranger. Is less than break time equals 1s, is greater than number, part 2, how you weigh emptiness. The hardest part of this entire story is the thing we have to do first, which is to detect something whose whole nature is absence. You cannot point a telescope at a void and take its picture. There is no glowing object to focus on, no edge that catches the light, no shape that announces itself against the dark. A void does not emit anything. It is not a thing so much as a thinning, a place where the ordinary furniture of the cosmos has been set out more sparsely than usual. So how on earth do you find one? The answer is almost comically simple in principle and fiendishly difficult in practice. You count. You count what is there, and you compare it to what should be there. Imagine walking through a forest and trying to decide whether a particular stretch of woodland is unusually sparse. You would not look for the missing trees, because missing trees do not exist to be looked at. Instead, you would count the trees that are present in a given area, and you would hold that number up against the average number of trees per area across the whole forest. If your stretch comes up short, again and again, in every direction you sample, then you can say with confidence that you are standing in a clearing, even though a clearing is made of nothing. This is exactly what astronomers do with galaxies. They survey huge regions of sky, they count the galaxies they find, they work out how far away each one is, and they build a three-dimensional map of cosmic density. Then they ask the forest question: is our region sparse? In 2013, 3 astronomers gave the clearest answer anyone had managed up to that point. Their names were Ryan Keenan, Amy Barger, and Lennox Cowie, and the void carries their initials because of what they did. They measured the density of galaxies and the amount of infrared light coming from the matter around us, and they mapped how that density changed as they looked further and further out. What they found was a deficit, a genuine, persistent shortfall in the amount of stuff in our cosmic vicinity. The region around us, they concluded, is significantly underdense compared to the universe at large. Their measurement put the difference at something close to half. In a shell of space, reaching from about 40 megaparsecs out to about 300 megaparsecs from us, the density of matter ran roughly half of the cosmic average, which works out, when you average the whole volume sensibly, to a region something like 20% emptier than it ought to be. Now, I have just thrown a unit at you, the megaparsec, and I do not want it to slide past without meaning, because the scale is the whole point. A megaparsec is about 3.3 million light-years. So when Keenan, Barger, and Cowie talk about 300 megaparsecs, they are talking about a distance of roughly 1 billion light-years. That is the radius of the underdensity, the distance from us out to its rough edge, which means the full span of it, edge to edge through the middle, is close to 2 billion light-years. Try to hold that in your mind for a second. A region of space, 2 billion light-years wide, and we are somewhere near the middle of it, and across that entire stretch the universe is thinner than average. This is the largest underdensity of its kind that anyone has ever measured. It is, in the most literal sense, the biggest known hole in the universe, and we appear to be living inside it. If that measurement stood alone, you would be right to be skeptical, and skepticism was exactly the first reaction. A single survey can be fooled. Maybe the count was patchy, maybe dust got in the way, maybe the corner of sky they sampled was unlucky. Science does not believe a strange result until something independent confirms it, and this is where the story gets sturdier. A separate line of work, led by astronomers Tom Shanks and his colleagues, including a careful analysis with a researcher named Whitbourne, went after the same question using a different method and a different catalogue. They counted around 250,000 galaxies, drawn from major sky surveys spread across most of the visible sky. They were looking for what they called the local hole, and they found it. Their numbers landed in a similar place, an underdensity of roughly 15 to 20% extending out to a few 100 million light-years and beyond, covering the overwhelming majority of the sky. 2 independent teams, 2 different techniques, 1 conclusion. The neighborhood is thin. I keep using that word, thin, on purpose, because the most common misunderstanding about a void is that it is empty, and I want to dissolve that picture right now. The KBC void is not a vacuum. It is not a clean bubble. We are inside it, and so is our entire galaxy, the Milky Way, with its hundreds of billions of stars. So is the local group, our little gathering of galaxies that includes Andromeda. So is the Great Virgo Cluster, with its thousands of member galaxies. The void contains an almost unimaginable amount of matter. It is simply that, compared to the cosmic average, it contains about a fifth less than it should. The emptiness is statistical, not visual. If you were dropped at the void's center and told to look around, you would see a perfectly normal-looking sky full of stars and galaxies. You would never guess you were standing in the largest known thinning of the cosmos. The shortfall only reveals itself when you count carefully and compare against the average, which is precisely why nobody noticed it for so long. But do not let the gentleness of 20% fool you into thinking it is trivial, because the scale magnifies it into something staggering. A 20% shortfall in a small room is nothing. A 20% shortfall across a sphere 2 billion light-years wide is a deficit of matter so large that the human mind has no real handhold for it. We are talking about the absence of the equivalent of countless galaxies, the mass of quintillions upon quintillions of suns, missing relative to the cosmic mean. It is one of the largest single departures from average that has ever been identified anywhere in the observable universe. And the fact that it sits centered, more or less, on us is either an extraordinary coincidence or a clue to something we have not yet understood. There was one more hint buried in those galaxy surveys, and it is worth flagging now because it will matter enormously later. When astronomers look closely at how the galaxies in our region are moving, they found signs that the galaxies are not simply sitting still in the cosmic flow. They appear to be streaming, drifting in a coherent way, as if being gently pulled outward. That kind of organized motion is not random noise. It is exactly the fingerprint you would expect if we were sitting inside the inner part of a void with all the surrounding matter tugging on us from the denser regions beyond the edge. Hold on to that image of an outward drift, that quiet streaming toward the walls, because when we come to understand how a void can fool our measurements, that motion turns out to be the key to everything. So this is where we stand. A slightly emptier neighborhood, confirmed by two independent methods, 2 billion light-years across, with a faint outward current running through it. It sounds, when you say it like that, almost boring. A thin patch of cosmos. So what? Who cares if there are 20% fewer galaxies in our corner of an unimaginably large universe? And that reaction is fair. On its own, an underdensity is a curiosity, a footnote, the kind of thing you file away and forget. The shortfall only becomes electrifying when you connect it to something else, to a problem that has been tormenting cosmologists for over a decade, a crisis so sharp and so stubborn that it has people questioning the foundations of physics. Because it turns out that a hole in space of just the right size would do something remarkable to the single most important number in all of cosmology. To see why, we have to leave the void behind for a little while and go meet the crisis it might solve. A number that simply will not agree with itself, is less than break time equals 1s, is greater than number. Part 3. The number that won't agree with itself. The reason anyone loses sleep over a thin patch of sky is not the void itself, it is what the void might explain. For more than a decade now, cosmology has been living with a crisis, a genuine and growing fracture, right down the middle of the field, and the void has emerged as one of the leading suspects for what is causing it. So before we can put the void on trial, we have to understand the crime. We have to meet the number that will not agree with itself. The number has a name, the Hubble constant, and despite the intimidating title, it describes something you can picture easily. It is, simply, how fast the universe is expanding. Almost a century ago, the astronomer Edwin Hubble made one of the most consequential observations in human history. He found that the galaxies around us are not sitting still. They are moving away from us, nearly all of them, and the further away a galaxy is, the faster it is receding. The universe, he realized, is growing. Space itself is stretching, carrying the galaxies apart like raisins in a rising loaf of bread. And the rate of that stretching, how much faster a galaxy recedes for every additional unit of distance you put between it and us, is the Hubble constant. It is the single most important number for understanding the size, the age, and the fate of everything. You would think a number this fundamental would be something we have simply measured and moved on from. We have been at it for 100 years. We have orbiting telescopes and exquisitely calibrated instruments. Surely by now we know how fast the universe is expanding. And here is the problem, the strange and maddening problem at the center of modern cosmology. We have two excellent ways to measure that number. Both are built on decades of careful work. Both are trusted by the people who use them, and they give two different answers. Not slightly different, stubbornly, persistently, irreconcilably different. The two answers refuse to meet in the middle, no matter how carefully anyone checks. Let me walk you down the first road, because the methods themselves are beautiful. The first way to measure the expansion rate is called the distance ladder, and it is exactly what it sounds like, a series of rungs, each one calibrated against the one below it, carrying us out to ever greater distances. The lowest rungs use stars called Cepheid variables, special stars that pulse in brightness with a rhythm tied precisely to their true luminosity. Because we know how bright they really are, we can tell how far away they must be from how dim they appear. Then, on the higher rungs, astronomers use a particular kind of stellar explosion, the type Ia supernova, which detonates with a known and consistent brightness, a standard candle visible across enormous distances. By climbing this ladder, rung by rung, out into the expanding universe, teams measure how fast galaxies are receding at known distances, and they arrive at a value for the Hubble constant of about 73 kilometers per second per megaparsec. You do not need to memorize the units. You only need the number 73. Now let me walk you down the second road, which could not be more different. Instead of climbing outward from nearby stars, this method reaches all the way back to the beginning of time. When the universe was very young, only a few 100,000 years old, it was a hot, glowing fog of particles. As it cooled, that fog cleared, and the light that was set free at that moment has been travelling ever since. We can still see it today, coming at us from every direction in the sky, a faint background glow called the cosmic microwave background. It is the oldest light in the universe, a baby picture of the cosmos, and encoded in the tiny variations of that ancient light is an enormous amount of information about what the universe was made of and how it was behaving. A satellite called Planck mapped that glow with extraordinary precision, and from it, scientists can calculate what the expansion rate should be. When they run that calculation forward to the present day, they get a value of about 67, 73 from the ladder, 67 from the ancient light, and there it is, the crack. The two numbers are about 9% apart. I know that 9% might not sound like much. In everyday life, if two people estimated the length of a room and came within 9% of each other, you would call that excellent agreement. But cosmology is not everyday life. These measurements are now so precise, the error bars so tight, that 9% is a chasm. The two values are not just different, they are confidently, defiantly different, each one measured to a precision that leaves no room for the other. For a long time, the natural assumption was that somebody had simply made a mistake. That is the sensible first reaction. When two careful measurements disagree, one of them is probably wrong, and given enough time, someone will find the error, fix it, and the numbers will fall into line. That is how science usually heals these wounds. But that is not what happened here. Year after year, both teams went back over their work. They hunted for systematic errors. They refined their calibrations. They cross-checked with new instruments and new methods. And instead of converging, the two numbers grew more confident in their disagreement. The gap did not close. It hardened. The measurements got better, the error bars shrank, and the two answers just stared at each other across the divide, each more certain than before. There is a way scientists quantify how seriously to take a disagreement like this, and it is worth understanding because it tells you why this stopped being a minor squabble and became a genuine crisis. They measure the disagreement in units called sigma, which is just a way of asking how likely it is that the gap is a fluke, a random accident of measurement. A disagreement of 1 or 2 sigma is unremarkable, the kind of thing that happens by chance all the time. By the time you reach 5 sigma, the probability that the gap is mere coincidence has become vanishingly small, less than 1 in a million. 5 sigma is the gold standard physicists use to announce a genuine discovery. It is the threshold that was crossed when the Higgs boson was confirmed, and the disagreement between these two ways of measuring the universe's expansion has now reached around 5 sigma. In other words, the tension between the two numbers is, by the strict standards of physics, as statistically solid as a discovery. The universe is telling us, at the level of certainty we reserve for our greatest findings, that something is wrong. This is what the field calls the Hubble tension, and you can feel why it keeps people up at night. There are really only 2 ways out of it, and both are uncomfortable. The first possibility is that one of these 2 superb methods has a subtle flaw we have not yet found, some hidden error lurking in the distance, ladder, or in our reading of the ancient light. The second possibility is far more dramatic. It is that both measurements are correct, and that the disagreement is real, which would mean our standard model of the universe, the carefully built theory that ties the early cosmos to the present one, is missing something fundamental. One of those 2 answers has to be true. Either we are making a mistake we cannot find, or the universe is more complicated than our best theory allows. I want you to see that the void is not the only suspect here, because it would be unfair to the science to pretend otherwise. Cosmologists have proposed a whole lineup of possible culprits. Some think the answer lies in the early universe, in a brief burst of a strange substance called early dark energy that came and went in the first moments after the Big Bang, leaving its mark on that ancient light. Others suspect there were extra kinds of lightweight particles streaming through the young cosmos, subtly altering its behavior. Still others believe, quietly and persistently, that there is some systematic error in the distance ladder that we simply have not nailed down yet. Each of these ideas has its supporters, its papers, its arguments. The void is one contender among several, and any honest telling has to keep all of them on the table. Let me give you a way to feel the strangeness of this, because the numbers can go numb on you. Imagine you own 2 clocks, and you trust them both completely. One is a magnificent atomic clock, the other a precision instrument calibrated against the stars, and both have been tested for years and never found wanting. And yet every time you check them against each other, they disagree by several minutes, and the disagreement never goes away, never drifts, never resolves. You check and recheck. The clocks are perfect, and they cannot both be right, and neither will yield. After enough years of this, you would stop suspecting the clocks and start suspecting your understanding of time itself. That is roughly where cosmology finds itself. The instruments are too good, and the disagreement too stubborn for anyone to keep blaming a simple mistake. So the field has begun, reluctantly, to suspect something about the universe. And this is exactly the doorway through which the void walks in. Because there is one explanation for the Hubble tension that requires no new particle, no exotic burst of early dark energy, no broken telescope, nothing added to the laws of physics at all. It requires only one thing. It requires that the place from which we are measuring is not normal. What if the local measurement, the 73, is perfectly correct as a measurement, but it is local in a way that matters? What if the patch of universe we are measuring from is not a fair sample of the whole? What if we are taking the universe's pulse from inside something, and that something is making the pulse red fast? Connect this back to where we began, and the shape of the whole investigation comes into focus. The void only matters because of this number. The thin patch of sky we spent the last little while measuring would be a mere curiosity, a footnote, if not for the fact that an underdensity of just the right size could make our local corner of the universe appear to expand faster than the true cosmic average. It could take a genuine expansion rate near 67 and make it read like 73 to anyone measuring from the inside. The Hubble tension, in other words, is the motive. It is the reason the void is on trial at all. The crisis gives the emptiness its meaning, turning a quiet astronomical oddity into a possible answer to one of the great open questions in science. But a motive is not a mechanism. To convict the void, we have to understand exactly how a region of nothing could reach out and bend the most important number in cosmology. And the answer to that is so elegant, so quietly clever, that once you see it, you will never look at an empty room the same way again. Is less than break time equals 1s is greater than number part 4. Why an empty room makes the universe look fast. The question we left hanging is the one that turns this whole story from a curiosity into a possible solution. How could living inside a hole make the universe appear to expand faster than it truly does? It seems, at first, like it should not matter at all. Expansion is expansion. Space is stretching everywhere, carrying galaxies apart, and surely it does not care whether our particular neighborhood is a little thin. But it does care, and the reason comes down to gravity and to the simple, relentless way that matter pulls on matter. Gravity is an attraction. Everything with mass pulls on everything else with mass. We learn this as children and then mostly stop thinking about it, but the consequences for a void are profound. Consider where the matter is. Inside the void, the region is thin, underdense, with less stuff than average. But the void has edges, and beyond those edges, out in the surrounding universe, the density climbs back up to normal and beyond. The walls of the void, the regions around its rim, are denser than its interior. So now ask yourself, if you are a galaxy sitting inside the void, which way does gravity pull you? It pulls you outward, toward the denser walls, where more mass is gathered. The emptiness at the center has less gravitational grip than the fuller regions outside. And so, slowly, over cosmic time, the matter inside a void drifts outward, drawn toward the richer surroundings, leaving the void emptier still. This is the outward streaming I asked you to hold on to earlier, the coherent drift that astronomers actually detected in the galaxy surveys. It is not random. It is the gravitational signature of the void, every galaxy inside being gently tugged toward the walls. And here is where it gets clever, where the trick reveals itself. When we look out at the nearby galaxies and measure how fast they are receding from us, we are not measuring pure cosmic expansion. We are measuring cosmic expansion plus this extra outward drift. The two motions add together. The galaxies are flying away from us, both because space itself is stretching and because they, and we, are being pulled outward toward the void's denser edges. So, picture what that does to our measurement. We see nearby galaxies receding, and we naturally interpret all of that recession as the expansion of the universe, because that is what recession usually means. But part of it is not expansion at all. Part of it is the void quietly draining outward, adding speed to everything we see. From our seat inside the hole, the local universe looks like it is expanding faster than it really is, because we are mistaking the void's outflow for cosmic stretching. Our speedometer reads high. And we have no obvious way of knowing it, because from the inside, the outflow and the expansion look identical. They both just look like galaxies moving away. Let me give you a way to feel this in your body, because it is the kind of idea that clicks the moment you find the right picture. Imagine you are trying to measure the speed of a wide, slow river by standing at one point on the bank and timing how fast the water passes. But you happen to be standing at a place where the river narrows, squeezing through a gap between two rocks, so the water there is rushing much faster than the river's true average pace. You time the rushing water, you write down a number, and you declare that the whole river moves that fast. But you are wrong. You measured a local quirk and mistook it for the global truth. The void does exactly this to us. We are standing at a spot where the local flow is unusually quick because we are being carried outward by the emptiness, and we have been assuming that quickness is the speed of the entire cosmos. Now bring back the two numbers from the Hubble tension, because this is where the elegance becomes almost suspicious. The early universe measurement, the ancient light read by Planck, gives us the true global expansion rate, around 67, because it samples the whole universe at once and is not fooled by any local quirk. The distance ladder measurement, the 73, is taken right here, from inside our neighborhood, exactly where the void's outflow would inflate the reading. And the amount by which a void of the measured size and emptiness would inflate that local reading turns out to be just about right to push a true 67 up to an apparent 73. The gap that has tormented cosmology for over a decade could close. Not because of any new physics, not because anyone made a mistake, but simply because we have been measuring the universe from inside a hole and forgetting to account for the slope we are standing on. This is what makes the void hypothesis so attractive to the people who champion it. Chief among them the astrophysicist Indranil Banik, who has argued the case in careful detail across a series of studies. The appeal is its economy. Every other solution to the Hubble tension asks you to add something to the universe, a new particle, a new field, a new wrinkle in the early cosmos. The void asks you to add nothing. It asks only that you take seriously where we happen to live, and that you correct for it honestly. It is the explanation that requires the least and explains the most, and in science, that kind of economy is always seductive, even when it turns out to be wrong. But I have to be honest with you, because the people doing this work are honest about it too. For this beautiful mechanism to actually solve the Hubble tension, the void has to clear a high bar. It has to be large enough, and it has to be empty enough. A small, shallow underdensity would only nudge the local measurement by a little, not nearly enough to close a 9% gap. To do the full job, the void needs to be both enormous in extent and substantial in its emptiness. And whether the real void measures up to that demand is precisely the question the field is fighting over right now. The mechanism is sound. Gravity does pull matter out of voids, and that outflow does inflate local measurements. Nobody disputes the physics. What they dispute is the size of the effect, whether our particular hole is empty enough and wide enough to be the whole answer. There is a subtlety worth pausing on, because it tells you why this effect is so easy to miss and so hard to rule out. The void's outflow is not something any single galaxy advertises. No galaxy near us is flying outward at some dramatic, obviously suspicious speed. The drift is gentle, a small, additional velocity layered on top of the much larger cosmic recession, the kind of thing that hides inside the noise, unless you look at thousands of galaxies at once and ask whether they share a coherent tendency. And when you do that, when you average over enough of the sky, the pattern surfaces. The galaxies are not moving randomly. They lean, ever so slightly, outward, altogether, in the way that only a surrounding underdensity would produce. It is a whisper written across the whole local universe, inaudible in any one voice but unmistakable in the chorus. This is also why the effect grows more important the closer you measure to home. Far out beyond the edge of the void, in the ordinary universe, there is no extra outflow, and the expansion rate you would measure there is the true one. But the distance ladder measurement, the one that gives the troublesome 73, is built precisely from relatively nearby objects. The Cepheids and supernovae we can see clearly and measure well. Those are exactly the objects most contaminated by the void's outflow. So the very precision that makes the local measurement so trustworthy, its reliance on close, well-studied stars, is also what makes it most vulnerable to the void's distortion. The better we measure locally, the more thoroughly we may be measuring the inside of our own hole. So we have a suspect with a clear motive and a plausible method. The void could fake the Hubble tension, and we understand exactly how. But a mechanism that could work is not the same as a mechanism that does work, and a good investigator does not convict on plausibility alone. The proponents of the void needed something more. They needed an independent witness, some entirely separate phenomenon, unrelated to galaxy counts, that could either confirm the void's existence or expose it as a fantasy. And in 2025, they found their witness in the most unlikely place imaginable. They found it in a sound, a single note struck at the very dawn of time, frozen into the structure of the cosmos and still faintly readable today. To understand how a sound can betray a void, we have to go back to the first moments after the Big Bang. Is less than break time equals 1s is greater than number. Part 5, the sound of the Big Bang. There is a sound buried in the structure of the universe. I do not mean that as a metaphor, or not entirely. In the first few 100,000 years after the Big Bang, the cosmos was not the cold, quiet place we know now. It was a furnace, a dense and glowing soup of particles and radiation packed so tightly that it behaved like a fluid, and like any fluid, it could carry waves, pressure waves, sound waves in the most literal physical sense, rippling outward through the primordial plasma. The early universe was ringing like a struck bell, and the way that ringing froze into place when the universe cooled has become, improbably, one of our most powerful tools for measuring where we live. To understand how a sound could betray our void, we have to understand how that ancient note got locked into the sky. Here is what happened. In that early furnace, gravity was trying to pull matter together into clumps, while the intense pressure of the radiation was pushing back, trying to smooth everything out. This tug-of-war set up oscillations, waves of compression and expansion spreading outward through the plasma at enormous speed, a fraction of the speed of light. Every little overdense spot in the early universe became the center of an expanding spherical wave, a shell of matter rushing outward through the glowing fog. And then, about 380,000 years in, the universe cooled enough that the fog cleared. The plasma turned into transparent gas, the pressure that had been driving the waves vanished, and the waves simply stopped, frozen where they stood. Each expanding shell of matter was left stranded at a particular radius, a particular distance from its center, like a ripple in a pond flash-frozen into ice. That frozen radius has a specific, knowable size. The waves all traveled for the same amount of time at the same speed, so they all stopped at the same distance, leaving a preferred separation built into the distribution of matter across the universe. Galaxies, which formed later from that matter, inherited the pattern. To this day, if you measure the distances between galaxies across the cosmos, you find a slight but real tendency for them to be separated by a particular length, the size of those frozen sound waves. That length is about 150 megaparsecs, which is roughly 490 million light-years. Cosmologists call this pattern the Baryon acoustic oscillations, a mouthful of a name that simply means the frozen ringing of the baryonic matter, the ordinary matter of the early universe. And it gives us something extraordinarily valuable. It gives us a ruler. This is the part I want to make sure lands, because it is the key to the whole witness. The size of those frozen sound waves is a fixed, known length. It was set by physics in the early universe, and it has not changed. So it functions as a standard ruler laid across the cosmos, a known distance we can recognize at any point in space and at any era of cosmic history. And the beautiful thing about a ruler of known size is that you can use it to measure expansion. If you look at galaxies near us and measure the apparent size of that frozen ruler, and then look at galaxies far away and measure it again, you can work out how the universe has stretched between those two distances. The ruler should look the same everywhere, scaled only by the universe's expansion. Unless, of course, something local is distorting it, and that is exactly what a void would do. If we sit inside an underdense region, the void's gravity and its outflow subtly warp how that fixed ruler appears at nearby distances. The apparent size of the baryon acoustic oscillation ruler, measured close to home, would be tugged out of true by the void in a specific, predictable way, different from how it looks far beyond the void's edge. So here is the test, and it is gorgeous in its logic. Take 20 years of measurements of that frozen sound wave ruler at many different distances, near and far. Ask whether the pattern of how the ruler appears to change with distance matches a smooth, ordinary universe, or whether it shows the particular warp that a local void would produce. Let the oldest sound in existence tell you whether you are sitting in a hole. In May of 2025, 2 researchers did exactly that. Indranil Banik and Vasileios Kalaitsidis published a study in the monthly notices of the Royal Astronomical Society, in which they gathered baryon acoustic oscillation measurements, stretching back across 2 decades of surveys, and tested them against the void hypothesis. The result was the headline that brought this whole idea roaring back into public view. The data, they found, favor a local void, one roughly 20% underdense, out to about 300 megaparsecs, the very same size and emptiness that the galaxy counts had suggested years earlier. And when they included that void in their analysis, the statistical tension in the measurements dropped dramatically, falling from about 3.3 sigma in a smooth universe down to somewhere between 1.1 and 1.4 sigma with the void. The disagreement, in other words, largely melted away once they allowed for the hole. They put it in a way that caught everyone's attention. According to their analysis, it was roughly 100 times more likely that we live in a void than that we live in a perfectly uniform region of space. That is the line that ran around the world. And in July of 2025, Banik presented the work publicly at the Royal Astronomical Society's National Astronomy meeting in Durham, which is why, for a few days that summer, news outlets everywhere were asking the same startling question. Is the Earth sitting inside a giant cosmic hole? The sound of the Big Bang, they reported, hints that it is. I want to make sure you appreciate why this mattered so much to the people studying it, because it is easy to let one more study wash over you. The power of this result is that it is completely independent of the galaxy counts. Counting galaxies and listening to the frozen sound of the early universe are 2 utterly different things. One is a census of light in the present-day sky. The other is the imprint of pressure waves from 380,000 years after the Big Bang. They share no instruments, no assumptions, no method, and yet they point at the same conclusion, the same size of void, the same emptiness, centered on the same place. When 2 completely unrelated lines of evidence converge on a strange idea, that is exactly the moment when scientists stop dismissing it and start taking it seriously. The void was no longer just a quirk in a galaxy survey. The oldest sound in the universe seemed to be whispering that it is real. But I have to hold the line on honesty, the same line the researchers themselves hold. Favoring a void is not the same as proving one. Reducing the tension from 3 sigma to 1 is a powerful hint, not a verdict. The result makes the void more likely, more credible, harder to ignore, but it does not close the case, and Banik and his colleagues would be the first to say so. The science here is alive, contested, and unfinished. What the study did was elevate the void from a possibility to a genuine contender, an idea with two independent witnesses now testifying on its behalf. And once you believe the void is real, once you accept that we probably do live inside an underdensity, the very next question is the one that gives our title its second half. Not whether the void exists, but how big it is. And the answer to that turns out to be where the whole story becomes truly difficult. Is less than break time equals 1s is greater than number, part 6, and it's bigger than we thought. The title of tonight's journey makes a promise in its second half, and now we have arrived at the place where that promise has to be kept. It is bigger than we thought. I have used that phrase in two senses throughout, almost without flagging it, and I want to pull them apart now because both are true and both matter. There is the physical size of the void, the sheer span of it across space. And there is the size of its consequences, the reach of what it does to our understanding. The void is bigger than we thought in both ways at once, and the two are tangled together. Start with a physical scale, because the numbers deserve to be felt rather than just stated. At its largest estimate, the KBC void stretches as much as 2 billion light-years from edge to edge. There is, as far as anyone has measured, no larger underdensity of its kind anywhere in the observable universe. We are not talking about a modest local thinning. We are talking about the single biggest known hole in the cosmos, and our address is somewhere near its center. To put that span into human terms, consider the light that is only now reaching one side of the void from the other. That light set out across the emptiness around the time complex life was first stirring in Earth's ancient oceans, and it has been crossing the void ever since, only arriving at the far rim about now. The void is so wide that a beam of light, the fastest thing in existence, needs a chunk of time comparable to the entire history of animal life on our planet just to cross it. Now turn to the other meaning, the size of the consequence, because this is what lifts the void out of the realm of trivia. A 2 billion light-year hole that merely sat there, affecting nothing, would be a fascinating piece of cosmic geography and little more. But this void does not merely sit there. If it is real at this scale, it reaches up and bends the single most important measurement in all of cosmology, the expansion rate of the universe. It takes the Hubble tension, that 5 sigma crisis that has resisted every easy answer for over a decade, and offers to dissolve it. A piece of local geography that can rewrite the apparent age and growth of the entire cosmos is not a footnote. It is, potentially, one of the most consequential features of our cosmic situation that we have ever identified. That is what bigger than we thought really means here. Not just wide, important. But I would be doing you a disservice if I let the story stay this clean, because the science is messier and more interesting than a simple triumph. Not everyone agrees the void is as large or as decisive as the most dramatic estimates suggest, and in the same year that the sound of the Big Bang seemed to confirm a giant void, another analysis pulled hard in the opposite direction. A separate 2025 study, using what are called direct distance tracers, methods that measure the actual motions and distances of objects around us, came to a far more modest conclusion. The velocity fields they studied preferred a void with a radius of only about 70 megaparsecs, which is roughly a tenth of the 300 megaparsec size that the galaxy counts and the sound wave analysis had favored. A tenth. Not a billion light-year radius, but something far smaller and shallower. What does a result like that imply? It implies that a void may well exist and may well contribute to the Hubble tension without being large enough to explain the whole thing on its own. In that smaller void picture, the local expansion rate the void produces lands somewhere around 70 to 72, which trims the tension without erasing it. The void becomes a partial culprit rather than the sole offender, one factor among several rather than the master key. And that is a genuinely different conclusion from the one the sound wave study reached, drawn from the same year by serious people looking at the same universe. This is not a case of cranks versus experts. It is a case of experts disagreeing sharply about the size and significance of something we can all agree is probably there. I want to be very clear about where this leaves us, because the honest answer is the interesting one. As of right now, this is an open, unresolved, fiercely debated question in mainstream cosmology. There is a camp that says the void is large and decisive, the elegant solution to the Hubble tension. There is a camp that says the void is real, but too modest to do the job, a contributor and not a cause. And there is a third camp that says the tension is not about a void at all, that the answer lies in new physics in the early universe, or in some error we have yet to find. These camps are arguing in the pages of the same journals, at the same conferences, using the same data, and reaching different conclusions. That is not a weakness in the story. That is what live science actually looks like, in the moment before it settles. And yet, notice what even the skeptics concede. Almost nobody in this debate denies that some underdensity surrounds us. The galaxy counts are too consistent, the sound wave hint too suggestive, for anyone to claim our neighborhood is perfectly average. The fight is not over whether the void exists. The fight is over how empty it goes and how far it reaches, whether it is 1 billion light years or a few 100 million, whether it can solve the whole crisis or only part of it. The core of the title's claim survives every version of the argument. We probably do live inside a hole. Our measurements probably are shaped, to some degree, by the emptiness around us. The only open question is one of magnitude. So, we have established, as firmly as the current science allows, that we likely inhabit an underdensity, and that its size is both impressive and contested. But this raises a question we have so far skipped over, and it is one we need to answer before we can judge whether our situation is ordinary or extraordinary. Where do voids come from in the first place? Is a hole in the cosmos a freakish accident, a rare scar in an otherwise smooth universe, or is emptiness somehow built into the structure of everything? Because the answer changes how we should feel about our own void entirely. If voids are rare, then living in the biggest one is a staggering coincidence that demands explanation. But if the universe is full of them, if emptiness is the rule rather than the exception, then the real question becomes something else entirely. To find out, we have to pull back from our own neighborhood and look at the largest structures in all of creation, and at how the universe came to look like foam is less than break time equals 1s is greater than number. Part 7. How the universe turned to foam. To understand whether our void is ordinary or extraordinary, we have to stop looking at our own neighborhood for a moment and take in the whole architecture of the cosmos, the grand structure into which our void fits. And when you do that, you discover something that turns the entire question on its head. Voids are not rare. Voids are not accidents. The universe, on its largest scales, is built out of emptiness. To see why, we have to go back to a time when there was almost no structure at all, when the cosmos was as smooth and featureless as it would ever be. In the beginning, shortly after the Big Bang, the universe was very nearly uniform. If you could have looked at it then, you would have seen an almost perfectly even spread of matter, the same in every direction, with only the faintest imperfections. And I mean faint. The variations in density from one place to another were about 1 part in 100,000, a roughness so slight it is hard to even call it lumpy. The early universe was the smoothest thing that has ever existed, a near-perfect haze of matter with only the gentlest ripples disturbing it. Everything that exists now, every galaxy, every cluster, every void, grew from those whisper-thin variations. How do you get from a nearly smooth haze to the structured universe we see today? The answer is gravity, working patiently across billions of years. Gravity is an amplifier of differences. Wherever the early universe was very slightly denser than average, That spot had a little more gravitational pull, so it drew in matter from its surroundings, growing denser still. And wherever the universe was very slightly thinner than average, it had a little less pull, so it lost matter to its richer neighbors, growing thinner still. The dense got denser, the empty got emptier. A tiny initial difference, fed by gravity over cosmic time, grew into an enormous one. The faint ripples deepened into a dramatic structure, and the structure has a shape. That shape is one of the most beautiful and unexpected discoveries of modern astronomy. The matter of the universe is not spread evenly, and it is not gathered into isolated blobs either. Instead, it is collected into a connected network, a tracery of filaments and sheets and walls, with galaxies strung along them like droplets of water caught on a spider web. Where the filaments cross, you find the great clusters of galaxies, the densest knots in the whole structure. And in between the filaments and the walls, occupying most of the room, sit the voids, enormous rounded emptinesses, where almost nothing lives. Cosmologists call this the cosmic web, and when you map it out, the universe looks unmistakably like foam, or like the inside of a sponge, a network of thin walls surrounding huge hollow bubbles. The scale of this architecture is difficult to absorb. The filaments and voids that make up the cosmic web are the largest structures in the known universe, stretching across hundreds of millions of light years, some of them well beyond 1 billion. They are bigger than galaxies, bigger than clusters of galaxies, bigger than almost anything else you could name. They are the framework on which everything else is hung, the grand skeleton of the cosmos. And the most counterintuitive fact about this skeleton is how much of it is empty. If you picked a random point in the universe and asked what is there, the overwhelmingly likely answer is nothing, or nearly nothing, because the voids take up most of the volume. The galaxies, the stars, the planets, all the glowing matter we tend to think of as the universe, cling to the thin walls between the holes. The bright stuff is the exception. The emptiness is the rule. There is a detail in this growth process that makes voids even stranger to think about, and it bears directly on our own. Voids do not just sit passively once they form. They actively grow, and they grow because of the same outward pull we have already met. Matter inside an underdense region keeps draining toward the denser walls, which means a void gets emptier over time, hollowing itself out as the eons pass. And as neighboring voids expand, the thin walls between them can thin further and break, so that neighboring voids merge into still larger ones, the way two soap bubbles can join into a bigger bubble when the film between them pops. The emptiness is not static scenery. It is a slow, relentless process, the cosmos steadily sorting itself into ever emptier hollows separated by ever thinner walls. Over the full age of the universe, this sorting has built the foam we see, and it is still going on, the voids still swelling, even now. It helps to picture the whole structure at once, the way the great cosmic surveys have finally let us do. Map enough galaxies across enough sky, and the foam leaps out at you, undeniable. Long, thin filaments of galaxies stretch for hundreds of millions of light years, meeting at bright clustered junctions, with curving walls of galaxies draped between them like sheets hung out to dry. And everywhere, taking up nearly all the room, the dark, rounded chambers of the voids. It is one of the most ordered things in nature, and one of the most surprising, because nobody set out to build it. It assembled itself, gravity working on those faint primordial ripples for billions of years, with no architect and no plan. And the result is a structure that looks designed, a honeycomb of light and emptiness spanning everything we can see. So here is the realization that changes everything about how we should feel regarding our own situation. If the universe is foam, if most of space is void, then finding ourselves near a void is not strange at all. It would be stranger to find ourselves nowhere near one. Voids are the default scenery of the cosmos, the most common kind of place there is, which means the interesting question was never really whether we live near a void. Of course we do. Almost everyone does. in the sense that voids are everywhere. The interesting question, the one that actually carries weight, is whether our particular void is unusual, whether it is larger than the typical hole, deeper than the typical hole, and centered on us in a way that would make our address the genuine anomaly. The foam tells us that emptiness is ordinary. What it cannot tell us, on its own, is whether ours is ordinary too. And to start getting a feel for that, it helps to look closely at one of these great emptinesses, to see just how staggering a single void can be. Is less than break time equals 1s is greater than number, part 8. The Great Nothing. If I want you to truly feel what a cosmic void is, statistics will not do it. I need to take you to one. And the most famous void in the universe, the one that has haunted astronomers since it was found, sits in the direction of the constellation Boötes, the herdsman. It was discovered in 1981, and from the moment its size became clear, it has served as the standard against which all other emptiness is measured. They call it the Boötes void, though it has earned a darker nickname, the Great Nothing. And once you understand what is, and is not, inside it, the word void stops being abstract. The Boötes void is about 330 million light-years across. That alone is hard to picture, so let me give you the number that really lands. In a region of space that size, scattered across that enormous gulf, astronomers expected to find something like 2,000 galaxies, based on the average density of the universe. That is what a normal stretch of cosmos that big should contain. When they actually counted, they found about 60 galaxies where 2,000 should have been. The Boötes void is not a little thin. It is profoundly, shockingly empty, missing the overwhelming majority of the galaxies it ought to hold. It is one of the loneliest places we know of in all of creation. There is a line about the Boötes void that astronomers love to repeat, and it captures the strangeness better than any number can. If the Milky Way had formed at the center of the Boötes void, instead of where it actually sits, we would not have known that other galaxies existed until well into the 20th century. Think about what that means. The nearest galaxies would have been so far away, so faint, so sparse, that our early astronomers, looking up with their first telescopes, would have seen only stars, our own local stars, and, beyond them, apparent emptiness. The discovery that the universe is full of other galaxies, other islands of stars, one of the most profound realizations in human history, simply would not have been available to us. We would have believed our galaxy was the entire cosmos, alone in the dark for far longer than we did. The void would have hidden the universe from us. I bring up the Boötes void not just because it is remarkable in its own right, but because it lets us calibrate our sense of scale, and the calibration is sobering. The Boötes void is genuinely one of the largest, emptiest single voids we have ever charted, a benchmark of cosmic emptiness, the Great Nothing itself. And yet our own KBC void, the one we appear to live inside, may be several times larger across than Boötes. Let that comparison settle. The most famous emptiness in astronomy, the one so enormous it could have hidden the universe from a civilization at its center, may be a fraction of the size of the hole we are sitting in. When you hold the two side by side, the claim of the title stops sounding like hyperbole and starts sounding like sober description. The Boötes void is not the only great emptiness out there either. The cosmic web is dotted with supervoids, some of them associated with peculiar cold patches in the ancient background light, regions where the cosmic microwave background appears slightly cooler than its surroundings, possibly because that light had to climb out of an enormous underdensity along its journey to us. These supervoids are scattered across the sky, each one an immense hollow in the foam. And even these emptiest of places are not truly barren. They contain rare, isolated galaxies, strange and solitary objects that formed and evolved in near total isolation, with no close neighbors to interact with, no cosmic society at all. There is a quiet rabbit hole there, the study of how a galaxy grows up alone in the emptiest places that could fill a night of its own. But I will leave it as a marker and pull us back to the thread. It is worth dwelling for a moment on what life is like for the few galaxies that do inhabit a place like the boat is void, because it sharpens the picture of just how empty can be. A galaxy out in the middle of a great void has no close companions. Across most of cosmic history, it has had nothing to collide with, nothing to merge with, nothing whose gravity it could feel in any meaningful way. The galaxies we know best, including our own, are shaped by their neighbours. The Milky Way is slowly drawing in smaller galaxies, trading material, distorted and fed by its companions, on a collision course with Andromeda billions of years from now. A void galaxy experiences none of that. It grows up in near total solitude, evolving on its own terms, in a quiet that has no real parallel in the denser parts of the universe. Studying these lonely galaxies is a window into how a galaxy develops when the cosmos leaves it almost entirely alone, and it is a reminder that emptiness is not just an abstraction on a map. It is a condition, a kind of cosmic isolation profound enough to shape the lives of whole galaxies. And the great emptinesses leave fingerprints we can read even from across the universe. When light from the early cosmos passes through an enormous underdensity on its long journey to us, it can lose a tiny amount of energy climbing out the far side, arriving very slightly cooler than light that travelled through ordinary regions. Astronomers have found a famous cold patch in the ancient background light, and one leading explanation is that the light crossed a supervoid on its way here. Whether that fully accounts for the cold patch is still argued, but the principle is sound and important. Voids do not just fail to emit light of their own, they actively, subtly stamp themselves on the light that crosses them, which is one more way these regions of apparent nothing turn out to be doing something after all. Because here is the contrast that matters, the one that brings us straight back to where we live. The boat as void, and all the great supervoids, are things we observe from the outside. We look across enormous distances and see them out there, hollows in the distant foam, and we marvel at them, precisely because they are over there, somewhere else, not here. But the KBC void is not something we observe from the outside. It is the one void in all the universe that we are inside of, looking out. And that single difference is the entire game. A void big enough to hold the universe at arm's length, centered on us, distorting the very light and motion we use to measure everything while we sit unaware in the middle of it, mistaking its outflow for cosmic expansion. That is the extraordinary claim. Not that voids exist, they are everywhere, but that we live in the belly of an unusually large one, and that it has been quietly editing our view of the cosmos all along. And if that is true, it leads to a problem that is, in its own way, even more unsettling than the Hubble tension. Because a void this big, centered on us, may be a place the rules of cosmology say should not exist at all, is less than break time equals 1s, is greater than number, part 9, a place that isn't supposed to exist. There is a twist in this story that the proponents of the void do not shy away from, and it is one of the strangest features of the whole affair. The very thing that might solve one crisis appears to create another. Because when you ask whether our standard model of the universe actually permits a void as large and as empty as the one we seem to inhabit, centered conveniently on us, the answer that comes back is troubling. According to the rules we think govern cosmic structure, a void like ours should be extraordinarily rare. It is, in a real sense, a place that is not supposed to exist. To see why, we need to understand what the standard model predicts. The reigning theory of cosmology goes by the shorthand lambda CDM, which stands for a universe made of cold, dark matter and a mysterious dark energy, represented by the Greek letter lambda. It is an enormously successful theory. It explains the ancient background light, the overall expansion, the broad pattern of how galaxies are distributed, all with remarkable accuracy. And one of the things it predicts is how often underdensities of various sizes should occur. Small voids should be common. Large voids should be rarer. Truly enormous voids, the size of the KBC void, should be vanishingly rare, almost forbidden, the kind of thing you might not expect to find anywhere in the observable universe, let alone centered right on top of us. In 2020, a group of researchers, Moritz Haselbauer, Indranil Banik, and Pavel Krupa, made this tension explicit in a study that has shaped the debate ever since. They argued that the KBC void, taken together with the Hubble tension it might explain, contradicts the standard lambda CDM model on the largest scales. Their point was sharp. If we genuinely live inside an underdensity this big and this empty, then according to the standard model, we got astronomically, almost absurdly, lucky to find ourselves there. The odds against it, under the reigning theory, are severe. So either we drew an almost impossible ticket in the cosmic lottery, or the standard model is incomplete, missing some ingredient that would make such a large void form more naturally than the current rules allow. This is what raises the stakes from a measurement puzzle to a possible crack in the foundations. The void started life as a way to relieve the Hubble tension without invoking new physics. But if the void can only exist by violating the predictions of our best cosmological model, then the void itself becomes the new physics, the new anomaly demanding explanation. You solve one problem and inherit another. There is a certain grim humour in it, the way nature seems to refuse a clean answer, handing you a solution with a fresh problem stapled to its back. The same group that pointed out the contradiction also offered a possible way out, though it is a controversial one, and I want to flag it clearly as a minority position rather than the consensus. They suggested that a modified theory of gravity, known as Milgromian dynamics, or MOND, might allow such large structures to form more readily than standard gravity does. MOND is a framework that alters how gravity behaves at very low accelerations, originally proposed to explain the motions of galaxies without invoking dark matter. It has a devoted group of supporters and a great many skeptics, and it remains well outside the mainstream of cosmology. I mention it not to endorse it, but because it is part of the honest terrain of this debate. Some of the same people who argue most strongly for the void also argue that the void points toward a deeper revision of gravity itself. Whether they are right is far from settled. And of course, there is the other side of this argument, which deserves its due. Many cosmologists push back hard on the claim that the void contradicts the standard model. They argue that the void's size and emptiness have been overestimated, or that the statistical analysis exaggerates how unlikely it is, or that lambda CDM, with careful accounting, can accommodate a void like ours without breaking. The smaller void result we discussed earlier feeds directly into this counterargument. If the real void is only a tenth of the largest estimate, then it is far less threatening to the standard model, far easier to explain as ordinary cosmic variation. So even the question of whether the void is a problem for our theories is itself contested, layered on top of all the other contested questions. What I find genuinely worth sitting with is the shape of the dilemma, because it is so characteristic of how science actually advances. We are caught between two uncomfortable options. Either we live in a void so improbable that its mere existence challenges our best theory of the cosmos, or our best theory is wrong in some way we have not yet pinned down. One anomaly, forcing a choice between extraordinary bad luck and new physics. That is exactly the kind of pressure point from which scientific revolutions have sprung before, the small, stubborn fact that will not fit, that eventually cracks open a whole new understanding. Our void may be nothing more than a statistical fluke that better data will tame. Or it may be the loose thread that, when pulled, unravels something much larger. And it is that possibility, the idea that the lumpiness of the universe might be hiding something far bigger than a quirk in the expansion rate, that leads us to the most radical stretch of this entire investigation. Because if the standard model can be fooled by the emptiness around us about something as basic as how fast the universe is growing, a few physicists have begun to ask a far more dangerous question. What if that same lumpiness has been fooling us about the single most mysterious ingredient in all of cosmology? What if the dark energy that supposedly fills the universe, the force we credit with pushing it apart, is not quite what we think it is? To follow that thread, we have to step to the very edge of accepted science, into a place where even the clocks no longer agree. Is less than break time equals 1s, is greater than number, part 10. The clocks in the emptiness. I want to take you now to the most radical idea in this whole story, and I need to be honest with you from the very first sentence. What I am about to describe is speculative, contested, and firmly outside the mainstream of cosmology. Most physicists do not accept it, but it is a serious idea, proposed by a serious scientist, published in respectable journals, and it follows so naturally from everything we have been discussing that it would be a shame to leave it out. It begins with a simple, provocative question. What if the emptiness of voids does not just bias our speedometer, but has fooled us about the existence of dark energy itself? The idea is called the timescape model, and its chief architect is a physicist named David Wiltshire. To understand it, you have to start with the assumption that nearly all of cosmology rests on, the assumption we have been quietly circling all night. The standard equations that describe the expanding universe assume that the cosmos is smooth, that on large scales matter is spread out evenly enough that we can treat it as uniform. This makes the mathematics tractable, and for a long time it seemed like a reasonable approximation. But we now know the universe is not smooth. It is foam. It is filaments and walls and enormous voids, lumpy on the largest scales we can see. And Wiltshire asks what happens if you stop pretending it is smooth and take that lumpiness seriously in the equations. Here is where it gets strange, and where you may need to slow your breathing and let the idea unfold, because it touches something most of us never think about. One of the consequences of Einstein's theory of relativity is that gravity affects the flow of time. The stronger the gravity, the slower time runs. A clock buried in a strong gravitational field ticks more slowly than a clock out in open space. This is not science fiction. It is measured fact, confirmed by precise experiments and accounted for every day in the satellites that run our navigation systems. Now, apply it to the cosmic web. Inside a dense galaxy, where gravity is strong, clocks tick slowly. Out in the emptiness of a void, where gravity is weak, clocks tick faster. The voids and the galaxies are literally experiencing time at different rates. How different? This is the figure that makes people sit up. Wiltshire calculates that over the full history of the universe, the difference in elapsed time between a clock sitting in an empty void and a clock here inside the Milky Way could be as large as about 38%. 38%. That is not a rounding error. That means a void, left alone since near the beginning, may have aged dramatically more than we have, run through far more time, expanded through far more of its own history than a clock in a dense galaxy would record. The universe, in this picture, does not have a single age or a single expansion rate. It has many, depending on where you are standing and how empty your surroundings are. And here is the payoff, the part that makes this idea so dangerous to the standard picture. When you build a model of the universe that honestly accounts for these mismatched clocks, for the fact that the empty regions have run through more time than the dense ones, the averaged-out expansion can appear to accelerate, even with no dark energy in it at all. The apparent speeding up of cosmic expansion, the very thing we invented dark energy to explain, might be an artifact, an illusion produced by naively averaging a universe whose clocks do not agree. In this view, dark energy, the mysterious substance thought to make up around 2/3 of everything, might not exist. It might be a mirage, created by our insistence on treating a lumpy universe as if it were smooth. I have to keep stressing how contested this is, because it would be irresponsible not to. The mainstream view remains that dark energy is real, a genuine component of the cosmos, and most cosmologists are not persuaded by timescape. But the idea has not gone away, and it has had some support. In 2024, a group including Wiltshire published an analysis of distant stellar explosions, the same standard candle supernovae we met earlier, and argued that the data showed what they called very strong evidence, favouring the timescape picture over the standard one. Whether that holds up under scrutiny is exactly the kind of thing the coming years of observation will decide. For now it sits where it sits, a provocative minority position, not a proven truth. But notice how it connects back to everything we have been tracing, because this is why I brought you here. Our local void is not an isolated curiosity. It is one front in a much larger campaign against a single assumption, the assumption that the universe is smooth enough to measure naively. The Hubble tension, the giant hole we live in, the mismatched clocks of the timescape model, all of them are pointing at the same suspect, the lumpiness of the cosmos and what it does to observers embedded inside it. If that assumption of smoothness is wrong, then the void we inhabit is not the disease. It is merely the nearest symptom, the closest and clearest example of a problem that may run through all of cosmology. And that reframes our whole entirely. It is not just a quirk of our address. It may be a window onto a flaw in how we have been reading the whole universe. Is less than break time equals 1s, is greater than number, part 11, nowhere special, revisited. We have to come back now to something we touched at the very beginning, because the void forces us to confront it, and it runs deeper into the history of science than any telescope. For 5 centuries, one principle has guided our understanding of our place in the cosmos, so thoroughly that we barely notice we are leaning on it. It is the idea that we are nowhere special. The Copernican principle, named for the man who first dethroned the Earth from the center of the heavens, holds that we do not occupy a privileged position, that the universe looks essentially the same from any vantage point, that no observer sits in a special seat. It has been one of the most reliable guides in all of science, correcting our ancient vanity again and again. The void hypothesis, gently but unmistakably, pushes against that principle. To find ourselves near the center of a rare billion light-year underdensity is to find ourselves somewhere, after all. Not at the center of creation, nothing so grandiose, but in an unusual place, a place that is not a fair sample of the cosmic average, a place from which the universe genuinely looks different than it would from a typical spot. If the void is real, and as large as some claim, then we do hold an atypical vantage point, and the comfortable assumption that our view is representative quietly fails. We would have to admit that we are, in this one specific sense, living somewhere out of the ordinary. I want to be precise here, because this is exactly the kind of idea that gets twisted into something it is not. The void does not mean the Earth is the center of the universe. It does not restore any ancient notion of cosmic importance, and it certainly implies no purpose, no design, no reason we were placed here. It means only that we may live in an unusually empty pocket of space, near enough to its middle that the emptiness shapes our measurements. That is a statement about geography, not destiny. We are not special in the sense of being chosen. We are special only in the sense of being, perhaps, a little unlucky, sitting in a spot that happens to distort the view. The distinction matters, and it is worth holding on to, because the moment you blur it, you slide from science into something else entirely. Still, I think it is worth naming the discomfort honestly, because it is part of why this debate is so charged. Some of the resistance to the void hypothesis is not purely about the data, it is about the principle. Scientists have been burned before by the temptation to place ourselves at the center of things, and they are rightly wary of any idea that seems to make us special again. The Copernican principle has been so successful, so often vindicated, that violating it feels almost like a step backward, a return to a pre-scientific arrogance. And so there is an instinctive pull, in some quarters, to distrust a hypothesis that asks us to be even slightly exceptional. That instinct is healthy, mostly. But instincts are not evidence, and the universe is under no obligation to arrange itself for our philosophical comfort. So how do we get out of philosophy and back into fact, the same way we always do, with better data? And here the story turns hopeful, because this is one of those rare, profound questions that may actually have an answer within reach, not in some distant century, but soon. The tools to settle it are already in space and already collecting light. The European Space Agency launched a telescope called Euclid in July of 2023, an instrument designed specifically to map the structure of the universe in 3 dimensions with unprecedented precision. Euclid is charting the positions of billions of galaxies, building a map of cosmic density so detailed that it can measure the shape and depth of the matter around us directly. If there is a great void surrounding us, Euclid and surveys like it should be able to trace its edges, weigh its emptiness, and tell us, with far less ambiguity than we have now, exactly how big our hole really is. There is a second line of attack too, using those same exploding stars we keep returning to. Large, high-quality samples of distant supernovae, gathered in the thousands, can distinguish between a smooth universe, a universe with a local void, and the timescape picture with its mismatched clocks. Each model predicts a slightly different pattern in how the brightness of those explosions changes with distance, and with enough of them, measured well enough, the patterns separate. The data needed is demanding, but it is the kind of data we are now genuinely capable of collecting. Which means the question of whether we live in a void, and how large it is, and whether it solves the Hubble tension, may move from speculation to resolution within years rather than lifetimes. We are, quite possibly, the generation that will actually find out. It is worth appreciating how unusual that situation is, because most of the truly profound questions in science do not come with a delivery date. We do not know when, or whether, we will understand what came before the Big Bang, or what consciousness is, or whether life exists elsewhere. Those may remain open for centuries. But the question of the void is different. It is a question about the structure of the matter immediately around us, out to 1 billion light years, and that structure is exactly the kind of thing our current instruments are built to map. There is no missing technology, no impossible measurements standing in the way. There is only the patient work of charting enough galaxies and enough exploding stars, work that is already underway. So this is one of those rare moments when a question that touches the foundations of cosmology, that brushes against our place in the universe and the reality of dark energy itself, sits within reach of an actual answer. On a timescale, a person can wait out. We may not have to wonder forever. We may simply have to be patient for a while. And whether the answer comes back that we are special or merely unlucky, that the void is enormous or modest, that dark energy is real or an illusion, the void has already done something valuable to us. It has forced us to question whether our cosmic vantage point is neutral, whether the seat we measure from is a fair one. And that question leads in the end to the strangest thought of the entire journey, the one I want to leave you with as the night settles. What does it actually mean to measure a universe from inside one of its holes? Is less than break time equals 1s, is greater than number, part 12, a universe of holes. Let me gather the threads now. slowly, the way you would draw a blanket up at the end of a long day. We began with a shortfall, a simple, stubborn shortage of galaxies in the space around us, 1 in 5 missing from where they ought to be. We followed that shortfall to a name, the KBC void, the local hole, a thinning of the cosmos perhaps 2 billion light-years across, with us somewhere near its middle. We met the crisis it might solve, the Hubble tension, 2 superb measurements of the universe's expansion that refused to agree, a disagreement now as solid as a discovery. We understood the elegant trick by which an empty region drains outward under gravity and inflates the speed we measure, making the local universe look faster than it truly is. We listened to the frozen sound of the early universe and heard it favor the void. And we pushed all the way out to the mismatched clocks of empty space and the radical thought that dark energy itself might be a mirage. When you lay it all out like that, the central idea stands clear, fully assembled at last. We may live near the center of an enormous void, and if we do, it has been quietly shaping everything we thought we knew about how fast and how smoothly the universe grows. Not through any dramatic event, not through anything we could see or feel, but simply through the patient gravitational consequence of living in a place that is emptier than average, looking out through measurements we did not realize were tilted. The whole does not announce itself. It just sits there, all around us, gently editing the view, and we have spent a century reading that edited view as if it were the unvarnished truth. I owe you an honest verdict, as honest as the science allows, and here it is. The void is probably real. Too many independent lines of evidence, galaxy counts, and the sound of the Big Bang and the streaming of nearby galaxies point to some genuine underdensity around us for it to be dismissed. But whether it is large enough and empty enough to solve the Hubble tension all on its own remains genuinely unresolved, argued over by serious people looking at the same sky and reaching different conclusions. That is where the science honestly stands tonight. Not at a triumphant answer, but at a live and open question, with the tools to settle it finally in our hands. I find that more satisfying than any tidy conclusion would be, because it means we are watching a piece of cosmic understanding actually take shape, in real time, in our own years. But I want to leave you with something larger than the verdict, a shift in perspective that this whole investigation quietly offers. We tend to think of the universe as the bright things, the stars and galaxies and clusters, with emptiness as the mere backdrop, the nothing in between the somethings. The void hypothesis turns that picture inside out. Voids are not the backdrop, they are the main structure. Most of the volume of the cosmos is emptiness, and that emptiness grows with time, the voids swelling and merging as matter drains out of them into the walls and filaments. The far future of the universe is a future of ever greater hollowness, the bright matter pulling itself into ever sparser knots, while the emptiness expands to fill almost everything. Emptiness is not the absence of the cosmic story. Emptiness may be the cosmic story, the shape the universe was always growing toward. There is a humbling symmetry in all of this that I keep returning to. For most of human history, we assumed the Earth was the center of everything, and it took a long, painful intellectual revolution to dethrone us, to teach us that we sit on an ordinary planet around an ordinary star in an ordinary galaxy. We learned to expect averageness, to assume our view was the universal view. And now, having grown so comfortable with our own insignificance, we are confronted with the possibility that our location is not quite average after all, not because we are important, but because the universe is lumpier than we let ourselves believe. The lesson is not that we were right to feel special all along. The lesson is subtler and stranger. It is that there may be no such thing as a truly typical place from which to measure the cosmos, that every observer sits somewhere particular in some pocket of the foam, seeing a view shaped by their own surroundings. The dream of the perfectly neutral vantage point, the God's eye view of a smooth and uniform universe, may have been a convenient fiction all along. And that turns the lens back on us, on what we have been doing all this time. We are creatures who learn to understand the universe by counting its lights, by measuring the things that shine. It was the natural way to begin, but in doing so, we may have quietly forgotten to account for the darkness we are standing in, the emptiness that surrounds and contains us and bends the very light we have been counting. We built our picture of everything from the bright things, and the bright things, it turns out, are the exception. The whole is the rule, and we live in one. So here is the thought I will leave hanging in the dark for you, as you let the day fall away. To measure the cosmos honestly, we first had to discover that we might be looking out from inside a hole in it. That the emptiness around us is not nothing, not an absence, not a void in the dismissive sense of the word, but a genuine structure, perhaps the largest and most important structure of our cosmic lives, one we never noticed because we were too busy counting the stars. The universe is mostly emptiness, and for the first time in all of human history, we are learning, slowly and carefully, and with no small amount of wonder, how to read the silence.